All right, so we're on to the next section here. This is section 4.2. It starts on page 223. It's called Analyzing Graphs of Polynomial Functions. We're going to start with this location principle, okay, and it should make sense. It says if the value of a polynomial function f of x, remember that's y values, changes sign. So if we're going from negative to positive or positive to negative on our y values, when we go from one value of x to the next, and we're going to go by integers, just like 1, 2, 3, 4, 5, then there has to be a 0 between those two x values. Okay, and so then we'll look at it a little bit. I'm not going to read this part, but I'm going to say some stuff by looking at this picture. Right? It starts off, I guess I'm going to read this part. Suppose that y equals f of x represents a polynomial function. We're going to look at this. And then let's say there's two x values at a and at b, such that when we plug them into our function to evaluate it, when we plug in a, we get a negative y value, and when we plug in b, we get a positive y value. Now, we've already talked about polynomials being continuous, so we know that it's going to fill in this line right here. So again, when we picked the first number a, we got a negative y value. When we picked another x value b, we got a positive y value. So since it goes from negative y to positive y, somewhere in between there, it has to hit 0. And that's all we're doing, is just somewhere in between these two numbers, we're going to get a 0. We're not actually finding the zeros right now. Okay, so let's see this in action. It says determine the consecutive integer values of x between which each real 0 of this function is located. Then draw the graph. Okay, so some things that we should know by looking at this is that we have it's an even degree, it's a 4 specifically, and that it is a positive leading coefficient. So our graph is going to look something like this. Something like that could possibly happen. It says because f of x is a fourth degree polynomial, it will have as many as 4 real zeros, or possibly none at all, right? If all of this is above the x-axis, we'd have none. But then they plugged in they made a little xy chart for us, and they plugged some in. And, we're going to graph this, so I'm just going to put some points roughly where they would be. So negative 229 is like way up here. I'll put it right there. And then negative 1, 3, so right there. And then 0, 1, 1, negative 1, oops, that's close enough, 2, negative 3, 319 are way up here again, so 319, I'll put it right there. And then 4, 113, so it's way up here. Okay, so I just plotted the points that they gave us. But now it says using the location principle, there are zeros between x is 0 and x is 1. Why? Because the y value at 0 was positive, the y value at 1 was negative, so it had to hit the x-axis somewhere in between these two x values. And we also have a 0 between 2 and 3. Why? Well, because the y value at 2 was negative, the y value at 3 was positive, and so again, it had to go between, somewhere in between 2 and 3, the y value had to be 0. So now we're going to sketch it, and I'm just going to use my points and the idea that we just talked about. So it's coming down, and this is just going to be a rough sketch. So, somewhere in between there, it crosses the x-axis, and it comes way down, and it comes way back up. And so, who knows, maybe it does something like this way up there. All right, now it says use technology to check the locations of the zeros. Input the function into a graphing calculator to confirm that the function crosses the x-axis between those two things that we had just seen. Okay, so we're not looking exactly what those numbers are. We're just kind of locating them between two integers. And then they want to say this. They say this, because you guys could graph this. Now, I know if you're using Desmos, you can just touch on it, and it'll tell you, a decimal value. If you're using a graphing calculator, you could trace it and kind of get close. But if you go to the calc menu, which is at the very top, you can locate, if you hit the calc, it'll give you this menu, and you can click on 0. And then it's asking for you to be left of the 0 and right of the 0. And so you get your cursor a little left of where it's going to cross the x-axis, and you hit enter, and then a little right of where it hits the x-axis, and hit enter, and then hit enter again, and it'll give you these two estimates. All right, so let's take a look at the check. It says determine the consecutive integer values of x between which each real zero of this function is located, then draw the graph. Okay, well, I drew the graph first. I mean, but again, we're using this location thing. And so like the way it would work is I'm looking at it and I'm going to draw a little XY chart of what you would want to do. So you'd be coming down and you'd be plugging in like -3, -2, -1, 0, 1, 2, 3, and then you would be getting Y values out of all of these. I'm not going to plug those in, but what I will say is at 2, what is it? Let's see. Anybody. At 2, or I'm sorry, at -2, it looks like it is 10. And then at 1, or I'm sorry, at -1, why does it not let me get to -1? At -1, oh, that's right there. It's about -4. Again, it doesn't really make any difference, but right. So then we know between -2 and -1 there has to be a 0 because we went from positive to negative. And then you keep plugging in values, and then you can get to the fact that at 1, it's about, if I can get there, well, it's about 2. At 1, it's about -2. And then at 2, when we get to 2, it goes way up again. Well, so at 2, it gets to be about 26. So again, we went from negative to positive. So we know that in between 1 and 2, we have another 0. Okay, and so then you're supposed to use more. Of course, I would use the graphing calculator or Desmos, but we do something that looks like, right, -2, we're way up here. And at -1, we're all the way down here. 1, 2, 3, 4, we're all the way down here. And then at -2, 0, we got a point there. And then at 1, we go down to -2. And we get a little bit lower. I'm sorry, we went no, well, it goes a little lower. I put in -2, but and then at 2, it's way up here again. So then basically, it's going to look like that. Actually, I better get that a little bit closer. Come on. All right, so then really it should go at 1. Oh, yeah, so I got them off a little bit. So it comes down like this and goes like that. All right, so the next thing we're looking at is extrema. Well, again, we've done this before. Extrema occur at relative maxima or relative minimum of a function. Okay, so, this is point A is a relative minimum because it's like the valley. It comes down, it goes back up. And B is a relative maximum because, again, it goes up and then comes back down, right? I mean, that's just a relative, right? There's no absolute in here if you remember your terms. Just a relative minimum and a relative maximum. Okay, both points A and B are called extrema. The graph of a polynomial of degree n has at most n minus 1 extrema. Okay, so like kind of relate that to the shape of our graph. If we have an x cubed, let's say, then that means at most we would have 2 extrema. It could be, it doesn't have to be that many, but if we were looking for zeros, we could have at most 3. Okay, so you've got to keep those two things straight. All right, so then identifying extrema. So they say, okay, here's a function. Estimate the x-coordinates at which the relative maxima and relative minima occur. Notice that all we're doing is plugging in integers and getting their corresponding y values and making a quick sketch. Okay? Estimate the location of the extrema. So then they're saying, okay, well, the value of f of x at x equals -2 is 4. And it is greater than the surrounding points, being this point and this point, right? 4 is bigger than both -5 and 3. So that indicates that there is a maximum somewhere near x equals -2. Now, if you're looking at the graph, it's not exactly -2. It's somewhere in between -1 and -2. But we're just getting it near. The value of f of x at 1 is less than the surrounding points, indicating that there is a minimum near x equals 1. And in this case, it looks like it's actually right? It looks like it's just, that looks like a minimum there. So this is the other point that we're looking at. Again, -5 is smaller than -2 and 0. You can use a graphing calculator to find the extrema of a function and confirm your estimates. All right, so let's look at the check. It says use a table of values of this function to estimate, and again, we're just estimating, the x-coordinates at which the relative maxima and relative minima occur. So remember, we're looking for values that are bigger than the surrounding values. So then we're coming down here, and if you notice, right, starting at -3, and then all of a sudden we get all the way up to 9, and then we're back down. So we're at -2, we get to 9, and -12, we go up to 9, and then we come back down to 2. So it pretty much seems that there's got to be a maximum somewhere right here, because we were going up, way down here at negative, and right, this is what let's just take a look at the graph. Like, this is what it basically looks like. It goes way up, and then down, and then something like that, okay? And so I put in these values. I just did it on Desmos and looked at the graph, okay? But, we're able to do this by just plugging in values. If you ask me, you're crazy if you're not using the graphing calculator or Desmos to come up with these values, but, do what you need to. All right, so then it sure looks like, right, that right here, that's going to be a maxima, or at least it's really close. So then we have a maxima really close at -2. Okay, and that would be like roughly right there. And then it looks again as we're going through, right, we're down here at -3, right? Then we go up to 0, and then we come back down to -7. So it looks like somewhere right here, that we're going to get another maximum. Because again, we're just comparing the y values. All right, and so then we're looking at a minimum, right? Notice that we're here, we're getting lower, all of a sudden we go back up, right? So lower, lower, higher, lower, lower, higher. So then that implies that probably somewhere really close to here, we're going to have a minimum. Okay, so the total number of certified pilots in the United States is approximated by this crazy function here, where x is the number of years after 1930, that's important, and f of x is the number of pilots in thousands. Graph the function and describe its key features over the relevant domain. So if they didn't give me this chart already, I would totally be typing this in the graphing calculator or Desmos. But since they did, we have this information here. And remember, we're not going before 1930. We're starting at 1930. Oops, sorry. Okay, we're starting at 1930. Okay, and so that's why we're only in quadrant 1 right now. Okay, so again, the y value is pilots. We're not going to get negative amounts of pilots, and we're not going to get We're not going to go before 1930 because I assume that's when planes came about. All right, so then they plotted this out, and I'm going to have to go to the next page, but I'm looking at things that we've talked about. I'm looking like somewhere around here is a maximum, somewhere around here is a minimum. Okay, and so they say the domain and range of the function is all real numbers. Now I have issue with that because the domain is clearly all real, but the range, right, because all polynomials have a domain that's all real. The range of a normal function is of a normal function to the fourth power is not all real, but I'll give them a break. They're having a lot of trouble here lately. But because the function models years after 1930, the relative domain and range is, right, x has to be bigger than the year 0. Okay, that's in 1930. And if you look at our little our XY chart, apparently at year 0, there was about 7 or 8 pilots. And these are in the thousands. So I guess somewhere between 7,000 and 8,000 pilots. So I don't know when planes came about, but I guess we're not tracking before that anyway. All right, I have to go to the next slide. So you got to be able to flip back and forth. Okay, so I'm going to redraw the quick sketch just so we can kind of see it. So it kind of goes like this, and it kind of goes down like that. All right, so then they're saying there is a relative something between 1980 and 1990. So you guys got to flip back and forth. But 1980, right, we're comparing everything to 1930. So 1980 is 50 years after that, and 1990 is 60 years after that. So you got to go to your graph and look between 50 and 60 on the x-axis. And if you look up, it sure looks like there is a relative maximum there. And then another relative something is happening between 2010 and 2020. Well, again, we're comparing to 1930. So that's 2010 is 80 years later, and 2020 is 90 years later. So again, go back to the other page and look at the graph, and it sure looks like there is a relative minimum going on there. Okay, so now we're talking about end behavior, and they put this little arrow on there. You can go check. But as x keeps getting bigger and bigger and bigger, as we go out way to the right to positive infinity, it sure looks like the y value is going to positive infinity. Okay, and so now they're saying, let's look at the actual domain. And in the domain, the y-intercept is at 0, 7.708. Okay, and I got that off that chart. And in our relative domain, okay, so who knows what happens before 1930? Nothing of our concern. There is no x-intercept, okay? Because again, what that would mean is at some point in after 1930, there became negative pilots. That'd be the only way we'd have an x equals 0 if you're following the location idea. Now, I don't know what you'd have to do to the population of pilots to make them negative, but I don't know if I want to know. Okay? Okay, and so then eventually we're going to talk about symmetry. And so if you're looking at this one, it says the graph of this function, it doesn't have any symmetry at all. So it does not have symmetry. All right, so let's look at this check. Oh, I cut it off. I can still do it. That's fine. All right, so it says the number of quarters produced by the United States Mint can be approximated by this function, where x is the number of years since 2005, and f of x is the total number of quarters produced in millions. Okay, so our output is quarters in millions. Use a graph of the function to complete the table and describe its key features. Okay, so I'm going to pause this, I'm going to fill this out, and we're going to talk about it. Okay, so again, our x value is years since 2005, and our y value is the number of quarters in millions. Okay, and so again, I just put this in Desmos, pulled this off. You can plug it in and do it any way that you want, but this is the chart. And then it says describe the key features. So the relative domain, right? We're producing, we're just in the first quadrant because we're starting at year 0, and at year 0 we made what would that be? 3 trillion quarters or something like that. Okay, so then the relative domain. So what makes sense in our what makes sense for our problem domain would be x is greater than or equal to 0, which is 2005. Okay, and then the relative range is what is our lowest number that we have here? And so the lowest number that I see, I skipped one in my thing. There has to be a number right here. Sorry, so that's 482.4. Okay, so that's everything's off. Like this one goes to 0, to 2, to 4, to 6, to 8, to 10. Okay, sorry. So then the relative range, so we looked at the lowest number. We said, well, everything's got to be more than 482.4. All right, so there is a relative minimum. So again, where were we going? Were we higher and then went lower and then went higher again? So then a relative minimum would be at between the years 2011 and 2013. Okay, and so then we're using years between 2000 or from 2005. So we're going by twos here. So at 6 we were at at 4, which would be 2000. Where are we going? Started at 2005, 2009. So at year 6, right? 2000, we had this many, and then at 2013 we started going back up again. So we were high, went low, and then started going high again. So somewhere in between these 2 years we had a relative minimum. Okay, the y-intercept is whatever that top value is. The y-intercept would be 0,3215. The graph of the function has no symmetry. So it does not have symmetry. Does not have symmetry. And then is it safe to assume this trend will continue indefinitely? So basically what they're saying is, at some point, are we gonna have an infinite amount of quarters? So that is, the word the book uses is unreasonable. It's unreasonable to think that just because we started going back up in year 10 here, that means forever and ever we're just going to have more and more quarters coming out of our ears. Okay, so again, make sure you're graphing these. I would use a graphing calculator to plug in things into your table. This isn't about can you plug in numbers and get the right answer. This is about what is these answers doing for you.